In this video, we are going to speak about how to design the MIMO observer system. In this lecture, we just speak about the full order system, and if someone is interested in the so-called minimal order system, that should go to the appropriate literature. The full order MIMO observer is very simple and a typical way to design the observer. This is the block diagram, which is well known from the CISO systems, and the upper part contains the system which we would like to observe in this case. It has got the input vector u, the output vector y, and the state vector x, which we have to use because we are working on a state feedback system. So we have to use the vector x. But in many cases, we don't want to measure x, or in many cases, we cannot measure the values of x, but the system input and output can always be measured, and these two data can be put as input to the so-called observer system, which will generate x hat, and this x hat is the observed value of the state vector. The goal is usually the following: x hat should be closer and closer as fast as possible to the real value of x. The observer has three matrices, F, G, and H. This part is the dynamics, so how fast the observer is, or how stable the observer is depending on the matrix F. The other parameter matrix is G, which is with the input of the system, and the last one is H with the input of the system. So these are the three matrices that we have to design. And from the CISO systems, we know that F is equal to A minus G multiplied by C. H is equal to B. It is the same as in the CISO systems. And F must be stable and fast. F must be stable and fast. These two data, stable and fast, can be designed by the eigenvalues of the system, and in this case we are going to work with the observer polynomial, the characteristic polynomial of the observer. Of course, we are going to design it. So we have to give the eigenvalues of F, the eigenvalues of F, that is the eigenvalues of the observers, which give us how fast and how stable the observer can be. So it is the determinant of lambda multiplied by the identity matrix minus F. And if next I'm going to put F as A minus G multiplied by C. These are the same, of course. And next I am going to take the transpose of this matrix, but if we take the determinant of this matrix, we are going to get the same eigenvalues as in the last case. So the eigenvalues from here and the eigenvalues from here are the same. So the transpose is not important in this case. And then if we want to calculate the transpose of A minus G multiplied by C, we can do it in the following way: A transpose minus C transpose G transpose, because the transpose of G multiplied by C is equal to C transpose G transpose. And if we go back to the controller design for a moment, we used this kind of determinant, which I put here with red, and we can see that they are very similar. They are very similar. I mean, these two representations. So here we are going to use the transpose of A instead of A. In this place, we are going to use C transpose instead of B. And here we are going to use G transpose instead of K. But the system representation in the bracket is the same. That's why we are going to use the so-called fictitious pair, fictitious system, and we can obtain the same design technique as we used for the controllers because of this similarity. So it's a very important knowledge from this part. So how to design the observer? Let us imagine that we can have a software tool for the design of the controller. We can use exactly the same technique for the observer design, but how? First of all, we have got the system representation A, B, C, D with these matrices. The first step is to create the fictitious pair. So from A, we have to prepare A transpose. And from the matrix C, we have to prepare a transpose. This will be the B matrix of the fictitious system. So it's very important that in the controller design algorithm, we have to use A transpose instead of A and C transpose instead of B. And from these two data, we can obtain the controller matrix K. And from this fictitious controller matrix, we can get here, we can get the matrix J, which is the K transpose. Let's go back to here for a moment. And from this G, we can obtain F. So with the very last step, we can obtain all the three matrices, because H is equal to B, all the three matrices of the MIMO observer.